my research is titled Variations on the LSTM Architecture for the Classification of Cognitive Stimuli-Based EEG Signals for BCI Applications. So a brain-computer interface is a technological apparatus that essentially facilitates a user and a computer device to communicate via brain signals. This is commonly achieved by the means of an EEG signal, which essentially measures the electrical impulses from the brain. And the way I attempted to enhance these applications is through deep learning. Around the world, millions of people suffer from physical disabilities. And the tragedy of this is that their brains are entirely functional while they are entirely limited in their lifestyle and overall experience just by their physical disabilities. And this was my inspiration to pursue this research to help facilitate to help augment their lives and essentially help them overcome their disabilities. In this area, I've already explored various deep learning architectures in order to identify an optimal approach to building architectures to facilitate this. And what my prior research found was that LSTM architectures, essentially forming a sequence-to-sequence model that has been simplified to cater to this specific need, performs exceedingly well. So it was this that inspired me to focus my research towards the LSTM architecture. LSTM, as most of you would know, stands for long short-term memory, which is a type of artificial neuron based on the RNN architecture. And it has three gates, input, output, and a forget gate that allows it to maintain long-term dependencies and retain information better. So there are a lot of challenges that are faced by someone who tries to develop brain-computer interfaces. First is the complexity of the data. Looking at EEG signals, there's a lot of features and a lot of noise that comes in. And also extracting the features from this can be extremely difficult because these are very small signals that vary quite a bit. There's also the issue of the uniqueness of brains. Every individual has a unique brain, and this makes it extremely difficult to develop a generalized application. So a lot of times brain-computer interfaces have to be tailor-made to the individual they are built for. And for this reason, as well as the fact that we need, if we want to deploy this in real time for a person with a disability to use, there's the need for a lightweight model that is also extremely accurate. And with the complex data, this makes it very difficult to implement. So the methodology I proposed sought to utilize cognitive stimuli-based EEG signals, which is essentially data that has been created through what is called cognitive dissonance, where the subject is given stimuli that cause the brain to become extremely active in order to target all areas of the brain equally and get very well readable and understandable data to train a deep learning model. The signals were gathered using a G Nautilus brain cap, which has 16 features. And then this data was trained on a variety of LSTM networks in order to identify the best LSTM variation to construct a BCI application. So these variations were the vanilla LSTM, which is just a standard single layer LSTM network, stacked LSTM, which was multiple layers, 4 in this case, bidirectional LSTM, which takes time series data in both directions rather than just one, so we can see the data from both sides. And that was also done in a stacked architecture as well, with 2 bidirectional layers stacked on top of each other. And then there was the vanilla unstacked with an attention mechanism added. This was facilitated with pandas, numpy, keras, and all the typical libraries in Python that would be used for deep learning training. And this pretty standard approach to building deep learning architecture. Yes, so this is the general flow that I follow, which I won't go into in too much detail. So essentially, these are what the architectures look like for the vanilla LSTM, stacked LSTM, bidirectional LSTM, and LSTM with attention. So essentially, what we're building is a traditional sequence-to-sequence model, but removing the decoder side and replacing it with a softmax, since we're not trying to generate any sequential data, but instead take sequential data as input and then generate output of just a single classification. It's essentially a sequence-to-sequence model that has been cut in half and replaced with a softmax layer. So after training, the results showed a significant amount of promise. These are what I measured was essentially accuracy in F1 score. In order to determine, since we just have to directly classify, these were the most obvious metrics to use. These are the results for the vanilla LSTM, stacked LSTM, and the bidirectional LSTMs, as well as the LSTMs with attention mechanisms. And so this is the comparison of all of them to prior research done by other researchers in the area. Here I'm comparing not only the F1 scores, but also the number of parameters, because as I mentioned earlier, it is also essential to have a lightweight model, because these applications need to be deployed in real time. So not only need to be accurate, but need to be able to function very fast, and the smaller processor needed, the better, because it needs to be affordable, as well as the more compact we can make it, the better it is. So we can see that while prior research using LSTM with attention plus a CNN to enhance the accuracy, while it produced good, very accurate model, the number of features was also very high. So it was impractical to deploy in real time. While when we applied things like attention mechanism in the stacked architecture, we get a very moderately lightweight model while improving the accuracy all the way up to 94%. F1 score to 90.94. So we can see the best model essentially was the stacked LSTM, 64 cells per layer, with a attention mechanism as well. So this provides a powerful classification method for decoding the EEG signals and then classifying them into the different classes we had provided. So it proposes, what essentially my research proposes is a model, like a traditional sequence to sequence model with attention and then removal of the decode layer, and instead replaced with a simple softmax layer. So it's a very lightweight architecture, very simplistic architecture that also provides very powerful performance and can be quite ideal for brain-computer interface applications. So after building the described architectures, the results conclusively show the capabilities of LSTM architecture to provide an accurate and lightweight means to classify EEG signals. By augmenting the LSTM network with variations as described in this research, such as bidirectional and attention mechanisms, we can further enhance the capabilities of the LSTM neural network. And with these architectures, we are capable of understanding complex time series data. And this demonstrates potential for application in BCI technologies, as well as several other models for sequential data that require real-time application, and we need accurate but lightweight models. In the future, I hope to apply these to further fine-tune these models to increase the accuracy more, and then hopefully deploy these in real-time scenarios in technologies such as robotic limbs or wheelchairs that can be controlled with via brain-computer interface. Yeah, so essentially, my research has conclusively shown the capability of LSTM neural networks for converting human thought into machine actuation, and hopefully can be beneficial technology towards helping people with numerous physical disabilities around the world. Thank you so much.